Have you ever had trouble describing the shape of an object when it's not in the room with you? Or what if the object doesn't even exist yet? Mechanical drawing is a useful skill that fixes this problem. Mechanical drawing is an action that uses lines and numbers to produce mechanical drawings. A mechanical drawing specifically and unambiguously describes the shape of an object. A drawing is super handy when designing with a team or ordering parts for manufacture. Companies also use drawings as legal contracts. If a part is received that doesn't match the drawing used in the quote, the customer can refuse to pay. I used this drawing to order my first ever part for work. I was studying abroad in Germany and my advisor needed a bracket to hold a part in an experiment. I was supposed to place the order with a shop, but the machinists didn't speak English and we didn't have access to English 3D modeling software on short notice. I nervously handed this to the machinist and he turned it into a 3D model and printed it on the 3D printer no problem. So unfortunately, I don't have a picture of the actual part, but these two white brackets in the photo were ordered the same way that summer. So the goal of this video is to give you the ability to make drawings just like this that are descriptive and conform to industry standards. Let's go do it. Here's our plan for making the drawing. First, we're going to draw a geometry that captures the shape of the object. Second, we're going to apply dimensions to that geometry to describe the size of those different shapes. And last, we're going to apply tolerances and check that our drawing is correct and complete. The part we're going to draw today is this pin with a square head. Remember, our goal is to create a specific and unambiguous definition of its shape and size. One place we could start to draw this is a pictographic view, just like we see here. However, this is not ideal because this perspective distorts the features. The circular end of the pin is shown as an ellipse, and the rectangular faces are shown as parallelograms. We need another view that doesn't have distortion like this. What if we looked at the pin head-on from the direction of this red arrow? It would look like a circle and a square. This is called a 2D projection, and it's the core of how geometry is described in mechanical drawings. Here's the recipe for a 2D projection. Imagine a plane perpendicular to the viewing direction. Now, transfer all object edges and outlines to that plane. These projected edges and outlines comprise the 2D projection view, and that will be the start of our drawing. The first view you create when making a drawing is called the base view. The lines used to draw part geometry are called object lines, which are just thick black lines. Let's add some dimensions to define the shape of the pinhead. These linear dimensions are used to show the distance between two objects. Unless otherwise noted, it's assumed that the dimension direction is vertical or horizontal on the paper. To create a dimension, an extension line is used to extend a feature from the part geometry. The extension line gets close to, but it doesn't actually touch the object lines. Use a number and some arrows to show the distance between two extension lines. You can also dimension angles like this, but unless otherwise noted, it's assumed that lines intersect at 90 degrees, so you don't need to dimension the angles in this part. Here we show the diameter of the shaft. When you're dimensioning the diameter of something, this diameter symbol is used. If you are dimensioning the radius of a feature, this capital R is used. The arrow that's used to point the dimension at the feature is called a leader, and a leader is just used to apply notes and dimensions when a linear dimension isn't suitable. This part's looking good. We've shown the diameter of the shaft and the square shape of the head, but we haven't shown the length of the shaft or the thickness of the head. We need another view on this drawing where we can see those features, but that also means we need a system for including multiple views on the same drawing. Back in our 3D view, we want to look at this part from the right so that we can see the length of the shaft and the thickness of the head. We'll use the same recipe to make a 2D projection. We have the imaginary plane and we project all the lines over. That projection is looking good for dimensioning the length and the thickness, but one problem is that it's not on the same plane as the base view, so we can't draw them both on the same piece of paper. So what we do is we unwrap the new view so that it comes coplanar with the base view, and on paper it looks like this. We have our base view from before and we've added a side view, so we now have a multi-view drawing. You could also give them descriptive names like front view and right view if you want to. The two projections must be in the same scale. It doesn't matter how close or far away the new projection is from the base view, but what does matter is that the top and the bottom line up, and every single feature down the line lines up as well. Let's go into depth about good view selection. Proper view selection is a really important part of making a clear drawing. Take this R-shaped solid for example. Here are two technically valid projections of that R, But the problem with that is that they have multiple interpretations. So if I were to make a drawing of this R, I'd want to make sure to include a top view so that the shape of that R is captured on the paper. Here's an example. This is a flagpole holder type part. This top view is really great because you can see the diameters of all the holes and you can see the outer diameter of the sleeve. Now I want to add a right view to this drawing, but a problem comes up. This part has some holes in it and you can't see the insides of the holes when you look at the part from the right, which hasn't happened yet. So we need some type of line to show hidden features. And what's done is we use these dashed lines called hidden lines to draw features that are hidden from view. When you're selecting views for a drawing, you want to pick views that minimize the number of hidden lines you have to use to show a part. Also, when you're dimensioning, it's better to apply dimensions to object lines than to hidden lines. So great, now we're done drawing the geometry of this pin. Now we're going to move on and flesh out all the dimensions. On our new view, we can show the length of the shaft and the thickness of the head. This part's almost done, but we don't know the position of the shaft relative to the square head. A lot of circular and radial features like slots, shafts, and holes are positioned by their centers, which we can't show with object lines. So what's used are center lines. Center lines are these lines drawn with alternating long and short dashes, and they're used to show the centers of radial features and other lines of symmetry. We can dimension to the center line to show the position of the shaft. Alright, now this drawing is looking great. If I was working with a team, I could hand this drawing to my teammate and they'd know what I was thinking in my head. So on our plan, we've finished drawing geometry and we've finished applying dimensions. But before we get to the tolerances, I want to review everything we've learned and make a drawing fresh. All right, we're back. Last step we have on our pin is to apply tolerances. I mentioned earlier that this part is good for my team, but it's not ready for going out the door yet. If I order this part, there's no way anyone will ever make a pin that's exactly 10 millimeters long, or 5 millimeters, or 15.32. Anything specific isn't going to happen. You have to apply tolerances to your dimensions, which are like upper and lower limits for the parts that you'll accept. Here's a common way to show tolerances. I've added plus and minus signs to all the dimensions, plus and minus 0.05 millimeters. Here are some rough tolerance guidelines. If you measure something with a ruler, you know that dimension to about plus and minus 0.5 millimeters. If you print something on a well-tuned 3D printer, that's about a plus and minus 0.2 millimeter process. And finally, a high precision machine shop can cut parts down to plus and minus 0.05 millimeters. There are lots of ways to show tolerances. When you see it on a drawing, it's usually pretty straightforward what's trying to be said. I could list the actual upper and lower limit of the tolerance as on the left. Bilateral tolerancing is what I used earlier, or unilateral tolerancing as shown on the right. When you're applying tolerances, you have to think about how they add up and make sure you're using good tolerancing practice. For this drive shaft part on the top, I've toleranced each segment individually, and on the bottom I've toleranced all the shoulders off of one face. And the result is that using the top method, the total length of the shaft has a plus and minus 0.3 millimeter tolerance window. On the bottom it's plus and minus 0.1 millimeters. So the takeaway is when you're tolerancing something, think about what's most important to you as the designer and pick tolerances that minimize the size of the tolerance window for the features that you find to be the most important. Over-constraining is something to watch out for. When you apply dimensions and tolerances, every feature in the part needs to be dimensioned exactly once, and only once. Take the drawing of this R-shaped solid from earlier. The total height of this part has been redundantly dimensioned and toleranced. If you look on the left, the height appears to be 40 plus and minus 0.1 millimeters. But if you look on the right, the total height is 40 plus and minus 0.2 millimeters. So then the question is, what is the total height tolerance? It's not clear here. So to fix this, you have to get rid of one of the bad dimensions. So we could get rid of that one, and this fixes it. Now we know the total height tolerance is plus and minus 0.1 millimeters. Back to our drawing, we have bilateral tolerances and nothing is over-constrained. So we're done. This is a totally valid drawing. It's complete. We could take it anywhere and people would understand what we're trying to say. Now that we're done with this drawing, let's flesh out our mechanical drawing toolkit with some alternate views that are better at showing certain features. First, I'll talk about a cross-section. Sometimes it's good to see the inside of a part. So you might imagine a plane cutting a part in the region of interest. Here is that flagpole holder part from earlier. And then you have the plane called the cutting plane and go slice it open. The sliced material in the view is shown with these dense diagonal lines called section lines. On the parent view, a phantom line is drawn to show the location of the cutting plane. To notate the view, put some letters on the ends of the phantom line and arrows pointing in the view direction of the cross section. And over on the cross section, put a note that references back to the letters drawn next to the phantom line. Another useful tool is called a detail view, which is used if you have some small detail that you want to dimension, but it would be tough to clearly dimension the features in the given scale of the drawing. To make a detail view, draw a circle around the region of interest, and then break that region out somewhere else on the drawing and use whatever scale you like. When you're placing the detail view, place it somewhere where it's clear that the detail view is not meant to line up with anything else in the drawing, so it's not confused for a regular 2D projection. The last view I'll talk about is called a broken view. If you have a part with a very large or small aspect ratio that would be tough to fit on the page and keep at a reasonable size to show detail, you can use something called a broken view. To make a broken view, you can take your part, add some jagged lines in there, and break out material to keep the size how you'd like it. The important thing here is to just make it obvious where the break lines are and not make the break lines confused for object lines. So you can use jagged lines, you can use curvy, free-handed lines, as long as it's clear that it's not real geometry. Those are all the alternative view methods I have for you. I want to share some story from my experience. One time I needed a post for a load cell experiment, and I wanted this post to have flats on it so I could turn the post with a wrench. So I made a drawing like this and sent it out to the machine shop. The drawing is mostly correct, but the problem is the part that I got back was this part in red. Instead of having opposing flats on it, it had a thin neck turned into the center of it. So that was no good, and this cost a couple days because we had to send the parts back to the shop to get it fixed. So if I was doing a good job, I would have made a clearer drawing to get the part correct the first time. Of the 3 alternate view methods I discussed, which were cross-section view, detail view, and breakout view, which view do you think might have helped make this drawing more clear? I think a really good view to use in this case would be a cross-section view. Here, on the far right, I've taken a cross-section of the region of interest, which is the region with those 2 flats, and I've dimensioned the flats right on the cross-section view. If I had done this originally, I might have saved some time. So to do a good job at work, you gotta make good drawings. I've heard this system called an alphabet of lines. When you're drawing something, if you get lost, refer back to this slide. It has all the lines that we discussed, and it could inspire you about what to draw next. Now it's time to test your knowledge. Which solid is described by the following drawing? I'll give you some time to think. If you want more time, you should pause your video now because the answer is coming right. 3, 2, 1, answer. It's A. So think of it like this. If you were standing on this ledge facing away from the hole and you started walking down the ledge and down the leg of this part, when you got to the bend, you would turn left. If you look at part B, when you're walking down the ledge away from the hole, on B, that leg turns to the right, so it's A. Question 2. Find a feature on this drawing from earlier that's not fully dimensioned. I didn't have time to make this drawing perfect for this talk, so there's actually some dimensions left out of this drawing. Can you find any features that aren't fully dimensioned? Answer coming in 3, 2, 1, answer. It's the flats here. In the cross section, the distance between the 2 flats is shown. However, the distance from the edge of the shaft to the start of the flat and also from the edge to the end of the flat is not shown, so that needs to be in there. Thanks for watching. I hope this video makes you a better mechanical communicator, and maybe when you see trinkets around you in everyday life, to think about what views you would use to describe those things. I've included some useful links in the description, and please subscribe for more videos.